You know, if you think about it, what's the one core piece of installation, or what's the one core piece of material that's ubiquitous across the board, that ties everything that we install in the trade together?
Panel.
Wire.
Tape.
Duct tape. Oh, my Lord. Thanks, guys, appreciate that. Wire, right? We're wiremen. If you think about it, the most common thing that we do is we pull wire. So you would think that everybody in this room, because we pull wire all the time, you guys would know this shit like back of your hand, right? We're wiremen. Yet, for some reason, I think we seem to get this wrong so much that it's probably the number one reason for failing inspections. It's just having the wrong wire inspection on readers, right? And I think what it boils down to is that on this test, they're very specific, right? We're talking about strictly by the book, only what the question gives you and nothing else, right? And so, it's real easy to try to, I guess, add things to the question, in your mind and make conclusions that you're not allowed to do on this exam. Whereas in the field, maybe you might have the ability to make those assumptions because you can go check out and make sure you have those values, right? The other thing too is that we have a rule in the front of the book that kind of comes into play that we don't really have to worry about in the field because most of the stuff that we deal with has got a temperature rating that is pretty common. Let me get over here to my slides before I get too far. Don't even ask me what that is. I'm trying to figure out. Somebody told me it was a stinger, like for rodents or something. Yeah. Yeah, no, well, they've got the neutral conductor just jammed in, or the ground conductor just jammed into that, but they've got that phase conductor around that nail. I think it's a stinger, right? Rodent control or something?
It's a trap.
Just don't stick your finger on it. Anyway, when we're talking about wiring capacity, right? I think this is the biggest thing to try to get your mind shifted. We're not really talking about wiring capacity at all. What's the number 10 good for?
30 amps.
Number 10. Number 10. So you're telling me number 10 good for 30 amps, right?
Yes, sir.
Bullshit.
According to this book.
According to the book, it is. I know for a fact I can get 100 amps on number 10 all day long. I've done it. I had this job once.
So you're the one who put the nail in the board.
Hey, so I had this job where I basically failed my inspection because with a breaker, there's actually two different types of protection in a breaker. You have the thermal, right, which is what the handle type. So when you say 200 amps, we're talking about 200 amps with a thermal value or limit. But there's also an inrush or like a maximum current, right, interrupting value, right, which could be 10,000 amps, could be higher. And so Austin Energy has in certain areas a minimum rating of a main at minimum of 22.5 or 22,500 AIC. So I went to Home Depot and I bought one of those Homeline 200 amp Homeline panels, the real cheap ones. Yeah, you know what I'm talking about, right? It came with a bolt-on, like you couldn't change it out. You couldn't just snap it out, snap it in a different one. It was 200 amp bolt-on main breaker that was rated for 10,000 amps on the interrupting capacity.
Yeah, I know what you're doing that here.
Yeah, and so I put that on the outside of the house, and Austin Energy came to interview us. They're like, nope, can't do it. It's not rated high enough. Well, I had to order one from freaking El Salvador or someplace down in the middle of Central America, and it took about 6 weeks to come in. And so in the meantime, I've got people trying to move into this house. It's in summer, and the door's open, air conditioner running wide open. And what I did is I took 10-3 Romex, and I backfed it from my skid panel that I had out for the temporary power, right? Rolled it across the front yard, put it in the back, and just backfed it into that breaker and turned on power. I guarantee you they had at least 70 or 80 amps running on that thing all day long because they were moving into this house in the middle of summer, right? When I pulled that 10-3 off of that 6 weeks later, it still looked like a number 10. It didn't melt it. It takes like 2,000 degrees Fahrenheit to melt a number 10. Like it was still number 10, right? When I started rolling it back up and put it back in my truck, it sounded like I was rolling it across popcorn or something. It was cracking and stuff. So what happened here was it's not that number 10 is limited to 30 amps because that's not true. That number 10 held 30, 70, 80 amps, I promise you, all day long. It didn't deform that number 10 a bit. Now, it was a different color, right? But it was still the number 10. But what got shot was the jacket around that number 10 because the heat was too much for the dielectric properties of that Romex jacket, right? It was totally useless at that point. I could never hope to ever use it again. So really what we're talking about when we're talking about wire ampacity is we're not talking about wire ampacity at all. We're talking about the jacket's ability to withstand the heat that that particular wire at that particular value would create and put on that jacket. Does that make sense? It's really the temperature rating of the jacket or the insulation that I'm worried about. And so if you'll stop thinking about it related to the wire, number 10 only be rated for 30 amps, and start thinking about it more holistically as the jacket is what we're trying to protect and trying to keep the heat off the jacket, I think this stuff will make a little bit more sense to you, because we're going to talk about 60-degree column and 75-degree column and 9-degree column and all the stuff in Celsius, which all has to do with the rating of the insulation, not necessarily the actual wire itself, right? So if you'll keep that in mind, that'll help. The other thing to remember is that a long time ago, manufacturers took a look at the value of what it costs to put together a termination based at 75 degrees Celsius, right? So every single thing that you have in the trade, whether it be a wire nut or a Kearney, I started to say Kearney, you don't use split bolts anymore, Kearneys. When's the last time you used a Kearney? Yeah, exactly. Anyway, Polaris blocks, motor terminations, breaker terminations, all of them have a maximum temperature rating, right, from the manufacturer that says, look, this is the maximum size wire that can go on this termination, and this is the rating in Celsius of that termination, right? Everything. Even a mechanical lug has a value. And that 250 case mil mechanical lug right there would be rated at whatever the value of the 75 degree rated 250 case mil conductor would be. Because they looked at the 9-degree rating, or the value of a 9-degree, and what it costs to manufacture a value that would be heavy enough to handle 9 degrees Celsius worth of temperature, and realized that you don't really get that much gain for a lot more manufacturing costs. It's just not worth it. Makes no sense. So from an economic perspective, that 75 degrees Celsius is the sweet point, right? I don't think I've professionally ever seen a 9-degree termination, ever. Because there's really no point in doing it. To get a 9-degree rating on a branch circuit means that every single thing in that branch circuit have to also be rated 9 degrees. Not just the breaker, but every termination everywhere in the branch circuit would all have to be rated 9 degrees. It's just not worth it, and it's very unlikely you'd ever run across something like that, right? So when we're talking about temperature rating, remember everything you terminate has a value, and it's either going to be 60 degrees Celsius, 75 degrees Celsius, or 9-degree rating Celsius. And I'm just telling you right now, that's really not true, right? Almost everything you see nowadays in the field is going to be 75 degrees Celsius. That's just kind of the general range. I've seen some 60 degrees Celsius stuff that has been a long time, but some of those old general purpose contactor blocks were rated for 60 degrees Celsius on the terminals. So remember, when we're talking about a branch circuit and we're talking about wire ampacity sitting by itself on a shelf is not a real value that means anything to me, right? If I have a wire rated for 9 degrees and it's sitting on a shelf, then maybe that 9 degree means something, but it's not actually going to carry any current because it's not connected to anything, right? But the minute I take it off of the shelf and I connect it to something that doesn't have a 9-degree rated terminal, guess what becomes the maximum value for that wire? Whatever the lowest value that is connected to is, right? It's like a circuit or a chain link, I guess, and whatever the weakest link in that chain is going to be the maximum amount of pull you can put on the chain, right? Temperature rating is no different. Whatever the smallest value on a branch circuit is, the lowest value in that branch circuit is going to become the maximum value for everything connected to it. So remember, when we're talking about 9 degrees on a wire, we're not really using a value, we're talking about a value that exists because that terminal rating, if it's rated for 75 degrees, will become the maximum value of everything connected to it, including the wire. That makes sense? All right, so that makes you go, why do we have 9-degree rating anyway? Well, if you look on page 161, I think is it? Or no, 181. 310.16 is the table. 310.16. Yours may be a little bit different page, but it should be close to 187. I'm sorry, 187 for me, 189 maybe? 189. All right. At the very top of this table, and I will tell you, this is probably the most common table you use in the entire code book. I mean, it really is that common of a table. But you'll notice that you have 3 temperature columns on that table. You have the 60 degree first, 75 degrees Celsius next, and the 9 degree on the first 3, and the ones on the left are copper, and the ones on the right are aluminum. So you can repeat the same thing on the aluminum values there. So, all right, that's at the very top there. The next thing you'll notice is that you have wire insulation types listed under each one of them. There's a bunch of them under the 9-degree value, quite a few of them under the 75, and very little under the 6-degree column. Now, before we do anything else, before we go anywhere else, before we even talk about anything else, we need to go back and look at a couple of things. Number one, you see the temperature rating conductor says see table 310.4 at the top of the table. Let's look at that real quick because I think it's going to be interesting to discuss. If you go to page 180, for example, or 181. So 180 if you got the first edition, 181 if you got the second edition. Let's look at THHN, or should be THHW. THHW. So on this table, THHW says, all right, let's talk about something real quick. When we're talking about the values on a jacket, all of these letters mean something. The T is a thermoplastic, it's like a flexible PVC is what that T is, a thermoplastic heat resistant compound. It's flexible PVC basically, that's what that T stands for. If I have a single H in a jacket, like a THN or THW for example, that single H means that's heat resistant, meaning it's rated for 75 degrees. So a single H is a 75 degree rating as far as the conductors are concerned. And if I have two H's, it's high heat rated and that's 9 degree rating. So this tells me this is a 9 degree rated conductor. This tells me that's a 75 degree rated conductor. Does that make sense? Now, the problem with THHW, if you look on this table, is that there's actually two temperature values just to the right of the third column there. 75 degrees Celsius on the top and 9 degrees, and then it corresponds with the next row, or next column, which is wet location and dry location. So, in other words, they're telling you the W here in this jacket means I can put it in a wet location. Problem is that the minute I do, that becomes the same as what this is. So it's 90 rated in a dry or damp location, but it's only 75 degree rated if I put it in a wet location. Does that make sense? So if you go back to page 186 or 187 or 188, you'll notice that in the 75 degree column, there are THHW, XHHW, and XHWN that are also specifically listed in the 9 degree column. Those are the only three that are in both columns, but they're in both columns because they're all dual rated conductors. You can put them in a wet location, but the caveat is if you do, they become a 75 degree rated conductor instead of a 9 degree rated. So if I'm using any one of those three conductors, THHW, XHHW, or XHWN, the first question I have to ask myself is it a wet location? Because if it is, it's no longer a 9 degree rated conductor, and I'm looking at the 75 degree value for it as a maximum value. Make sense? So THHW, XHHW, and XHWN, those are the three that are dual rated. And so what I want you to do is, she passed out a copy of my code book as a handout that has the wire capacity stuff. It's my 2020, but it'll give you a good idea of the notes. This one right here. Oh. Okay. So if you want to pull that out, just kind of keep it aside. Those are the notes that I would consider to be the minimum notes to kind of help understand this table. You may or may not understand those notes, but we're kind of going to go through them as we go, and eventually I'd like you to transfer those to your own code book. Now, maybe a little bit different layout, but pretty much the same format. But you'll notice across the top of the page there on that handout, on the 75 degree column, what do I have written up there? No, above it. Wet. And above the 9 degree?
Dry.
It's specifically because of this right here, where if I use this conductor in a wet location, it's telling me by code that it then becomes a 75 degree rated conductor. So in other words, THHW in a wet location is a 75 degree rated conductor. If it's in a dry location, it's a 9 degree rated conductor. So I want you to write wet across the top of 75 and then dry across the top of 90, and you're telling yourself, hey, these three conductors I have to be careful of. I have to ask myself, is this location wet or dry? Depending on what that is, that will help you understand where to start with that conductor. Okay? That's the first thing, wet or dry. And that means specifically only related. You'll see I've got arrows that go down to the stuff that's highlighted. You don't have to draw those arrows, but it would be a good idea to highlight those three conductor types onto the 75 and the 9 degree, just so that you have them called out. Okay? All right. The -2 is also a way for a jacket to tell you it's rated for 90 degrees, but a -2 is equal to 9 degrees Celsius and wet or dry. There's not anything that's dual rated there. So if you have a XHHW-2, that's a 9 rated conductor all day long, wet or dry. Okay? It's also a way to take, like for example, THW, which is 700 rated conductor. THW-2 is a 900 rated conductor, so that -2 gives it that 90 degree value, but you only see it in the 900 column. All right, that's item number 1. All right, let's start in the very beginning of your code book, because remember, when we're talking about this stuff, we're talking about a holistic approach to the entire branch circuit. 110.14 is a really important section. 110.14C on page 65. 110.14C. Remembering that we're talking about the weakest link being the maximum rating. So wire sitting on the shelf could be rated for 9 degrees, that's fine. Good for it, right? But that's not a useful number, because I can't really look at that unless everything connected in a branch circuit is also rated for 9 degrees. So when we're looking at a branch circuit, I have to look at the entire thing, and whatever the lowest value on that branch circuit is becomes the maximum value for everything connected to it. So for example, 110.14C1A is saying, look, if I've got wire that's sized anything from a 14 gauge to a number 1, or rated for 100 amps or less, the code book's telling me I'm only allowed to use a conductor rated for 60 degrees Celsius. That's a big important note. Basically what they're saying is this right here is the maximum value that I'm allowed to use, because under number 2, conductor with higher temperature rating based off of 60 degrees Celsius and passing conductor size used, or number 3, which says conductors with higher temperature ratings if the equipment is listed and identified for use with such conductors. So if I have a terminal that's rated for 60 degrees Celsius, then I'm going to have to use 60 degrees Celsius for the wire itself as a maximum value, right? Because I can't exceed what the terminal rating is. Now this is telling me 60 degrees Celsius is maximum. Number 3 is telling me that if I have a 75 degree rated terminal, then I'm allowed to use a wire rated for 75 degrees is what that means. But it doesn't say anything about the 9 degree column anywhere, does it? It doesn't say later on use a 9 degree column. In fact, if I specifically notably absent. And then it goes on to tell you that motors, and this is important, motors that have a design letter B, C, or D are allowed to be considered 75 degrees Celsius. So motors that are design class B, C, or D. And sometimes you'll see them on a test question tell you have a design class B. That's important if you're sizing a wire, because that tells you that is a 75 degree rated termination, right? Otherwise, what's going to happen if I'm sizing anything size 14 gauge number 1, this code book is going to limit me to the 60 degree column whether I like it or not. Because I don't have the ability to go double check the terminal rating myself, so I'm going to have to assume 60 degrees is a maximum capacity of conductor, anything size 14 gauge to number 1. That's a lot. That's a lot of wire. I've got that kind of marked out here, up here basically, and it's either that or 100 amps or less. Either one would qualify. So that's what these brackets here are trying to remind you of, is that these are the maximum values for that wire based on the 60 degree column. I'm going to use a 60 degree column right here based off of anything that's sized from 14 gauge to number 1. That's going to be the maximum value, just because of that caveat there, 110.14C1A.
Hey, Mitch, you said to put wet for just those two, right? THHW.
THHW, XHHW, and then XHWN. That's one more was added this year. So
Okay.
XHWN is the third one.
XHWN?
No. Yeah, it's under both the 75 and a 900 column.
All right, cool.
All right, now, under page 65, or under that same section we were just talking about, under these motors, under B, it does say that if it's over 100 amps or it's larger than number 1, so in other words, 1 hour larger, then I'm allowed to assume a 75 degree rating, so I don't have to worry about that for larger conductors. So look at it like this. We got branch circuits under section A, then you got feeders under section B, if you will, right? Because the feeders are usually 100 amps or greater. So that's really mentally how I kind of try to remember it. If it's under 100 amps or it's 14 gauge to a number 1, 60 degree column is the maximum value unless I know for sure what that terminal is rated for. 75 degree column for feeders that are anything 1 aught or larger. Parallel conductors are always going to be 1 aught or larger. Feeders of any nature, 100 amps or 101 amps or more, I'm allowed to use 75. Again, Doesn't say a word about 9-degree conductor value. So if we go back to page 186, 187, 187 or 188, did you say? What's your
89.
189, 187 or 189. So you're looking at this table. I mean, you can't miss that 9-degree column, can you? It's the biggest column in the whole book, isn't it? It is, right? Oh my God, it's like a siren's call. And it's like, why would I put a 9-degree rate? I'm telling you guys right now, you can't use a 9-degree column as a final number. So you're thinking, well, why is it there in the first place? And my note that I have next to this 9-degree column is that I must derate it, because here's the deal. That 9-degree rating is there for only one reason and one reason only, and that's because I'm going to derate that number to move it lower, but it can't ever be more than what the 75 or the 6-degree column is, depending on what the wire size is. Does that make sense? I'll say it again. 75 degrees or the 6 degree, depending on the wire size, is the maximum allowable value for any conductor, period, right? The 9-degree column is only there so that the D rates don't hurt so bad, but I still have to end up at or below either the 75 or the 60, depending on what the wire size is. So that 9-degree column is never, ever to be used as a standalone value, ever. You can't ever use it to answer a question about the ampacity of the conductor, because it's not there for that purpose. It's only there for us to derate. So in other words, I can't use a 9-degree conductor value unless I have derating factors to apply to that number, because I have to get it to that 75 or 60 degree or less, one way or the other. Make sense?
Does that say maximum bind ampacity?
Hmm?
Right there, does it say maximum bind or final?
Final, yeah, maximum final ampacity. That red bar is supposed to be a remembrance to myself that that's the bar. There's never, ever an answer on the test question higher than that 75 degree value, period. It's just not going to be. When I'm done doing the math, everything, all the dust is settling, I've taken all the derating factors into account or whatever, I cannot answer a value more than that 75 degree column. And that's usually for feeders. Sometimes I'm in the 6 degree column if it's a smaller conductor, because of that rule that we just talked about a second ago. Okay? All right, so let's talk about that for a second. We're saying that because of the, I love this slide. You got Arnold Schwarzenegger, you got to protect the Terminator. Huh? Yeah, I hope you guys will remember that. That is basically the terminal is going to end up becoming the biggest bottleneck, really, if you think about it. It's not the wire capacity at all. It's going to be the termination that's really going to be your limit to the value that you're allowed to put on it. And that's what guys forget. We stop thinking about the terminal. We are only thinking in our minds about the ampacity of that wire, but the ampacity of that wire is not a real value. It doesn't mean anything until I connect it. It doesn't carry current until I put it on a wire nut, right? Or put it on a breaker terminal. But the minute I do that, then everything else in that branch circuit, whatever the maximum, or whatever the lowest temperature rating and anything in that branch circuit, becomes the maximum capacity for everything connected to it. So the wire by itself is only a starting point. I can't be above the 75 or 60 when it's all said and done as a final calculation. Okay? All right, so think about it like this. If I've got a branch circuit wire that's 100 amps or less, 14 gauge or 1 knot, 60 degree is my maximum value, we're not even talking about the 75, right? So if I had a number 8, let's say I had a single number 8, XHHW. All right, XHHW is one of those dual rated conductors. Not to worry about that, because if they give me an indication that in that question that is a wet location, then that automatically is no longer a 9-degree rated conductor. On my little sheet here, what I wrote, down at the bottom, I have 3. Go right ahead. Let's go. There's 3 questions I asked myself at the bottom of this page. And the first question is, I can't even think about the 9-degree rating, the value of the 9-degree column if the wire itself isn't rated for 9 degrees, right? So a THW, for example, if they gave me a number 8 THW, I don't really care if it's wet or dry, I don't care what. That's only a 75 rated conductor, right? So I can't use a 9-degree column with this conductor because it's not rated for it to begin with, right? So number 1, I have to have wire rated for 9 degrees to even consider it. So THHW, check, that's rated for 9 degrees, right? Next question I have to do is, remember, I have to be at the maximum of either the 75 or the 6 degree column. In this case, number 8 is what I was going to put there, sorry. Number 8 falls in this category of this lump of wire right here, does it not?
Yes.
So my maximum value that I'm allowed to assume for that is gonna be that of a 6-degree column. That wire is rated for 90 degrees, but I have to be at or below the 60 when I'm done with my math. So the 90-degree rating is there for us to start with our calculations so we can use a little bit higher value, but the derating values are down here at the bottom of the table under section 1, 2, and 3. Section 1 says, all right, you guys know where, the NFP headquarters is?
NFPA.
Mhm. It's in, somewhere up in not Michigan, Massachusetts.
Oh,
Quincy, Massachusetts.
okay.
You know where that's at? That's just down the road from Canada, isn't it?
Yes, it is.
Pretty much, yeah. Do you think that 86 degrees Fahrenheit is hot?
Nope.
No?
For sure.
I mean, I think 86 degrees Fahrenheit is a nice cold day, don't I mean, but you probably think 86 degrees kind of warm. I mean, you probably, what's the average temperature up there in Canada?
Summer, probably, I have to do 75. No, that's not harder than that.
Oh, yeah, no, they get up to 91.
Yeah. No kidding. Let's say, I know where you're going with this. Temperature, let's say. It's in the mid-90s, low to mid-90s.
Yeah. For us in summer, 108.
Yeah.
116?
What was the high last summer? It was something crazy, like I never heard of.
116 or 117.
Was it really?
No, it was,
We hit 120 and all that stuff.
yeah.
Really?
I believe, yeah, it's like 123 or something like
This
that.
book was written by Canadians, just saying, right? This is not a Texas value at all, right? Ambient temperature is basically the air surrounding your installation. If it's hotter than blazes, you're not gonna be able to dissipate the heat off that conductor as effectively as if it was a nice, cool, balmy 86 degrees Fahrenheit, right? And so this table is based off of 86 degrees Fahrenheit. My point is that might sound really hot to somebody in Massachusetts, but down here, that's not a hot number at all. But it does tell you that every single value on this table is suspect, right? Because it's not 86 degrees Fahrenheit around here. It's just not. Maybe a couple days of the year, the rest of the time it's hotter than blazes. So the wet bulb temperature is set out by ASHRAE's, and it says over here somewhere, I can't remember, it's, I think the fundamentals. It's ASHRAE Handbook of Fundamentals. It's published every 3 years. They have the wet bulb temperatures of all the major airports. In Austin, Bergstrom Air Force Base, it's 98 degrees Fahrenheit is what the average mean wet bulb temperature is. So 98 degrees Fahrenheit is what we consider to be our average ambient temperature here in Texas, or in Austin specifically. Houston is 99. This is several years ago. I mean, it may have changed by then, but I think Dallas is 97 degrees Fahrenheit. Either way, that's a hell of a lot hotter than 86 degrees Fahrenheit, correct? So anytime I'm in an installation where my ambient temperature is hotter than 86 degrees Fahrenheit, I have to take that extra heat load into account and derate the ampacity values here because I can't really carry the same amount of ampacity in this hotter environment that I can somewhere else where it's cooler. Example? Yep, so I'm gonna go back. Down at the bottom, I want you to write yourself a note. Now remember, if you're on page 187, the note you're gonna write down next to section number 1 where it says 310.15b, you're gonna put a note to see page 185. If you're on the newer edition, you're gonna put 187, okay? That way you have the page reference down there at the bottom. Ambient temperature, so anything they give me on the test that says, hey, your ambient temperature is 98 or 105 or whatever, that's my indication that note one down at the bottom of the table is coming into play. So if you go back to page 185 or 187, right?
Yes, sir.
Yours, what happened? No, page 188. No, you're right. No, you're right, it's 187. That's right. Okay, 187, no, so the bigger table that is on the bottom, or the table that's on page 188, whichever one you have like that one, put an X to that one. It's this, yeah, no, that's the good table. The one that's on the bottom there, so no, use that one, that goes to a different table.
188?
Huh? Page 188, yeah, don't use it, right? No,
Oh, free air.
You're on a different, so what I'm saying is, don't use this table, this is the table you want to use.
Oh, okay.
Good table, bad, good table, bad. Good table, bad, next to bad.
Depends on which one you have. You have, Okay, so you were actually just looking for a 310/15 B11.
Yeah, B11, that's right, 310/15 B11. Yep, that's good. This is
Supposed
good.
to lay it out slightly different.
That's bad, so put it next to that, we don't wanna use that table. I don't mean it's bad, it just goes with a different opacity table than the one we normally use, so I think it has to do with free air conductor or something. The table that you see in there, the 310/15 B11, that is the correct table, it matches up with the 310/15, or 310.16, okay?
The cool thing about, so we can get the link to this video?
Yeah.
Okay.
Yeah, it's confusing now, but later on, watch it if you're
Man.
All right, now,
Taking notes, it's hard.
what that table has to do, it has the same 60 degrees, 75 degree, and 9 degree values that you saw on the other table, right? So depending on what column I take a value from on the other table, on page, or on 310.16, I have to use the exact same temperature column here to pick the derating factor that I'm gonna use to derate the conductor, okay? So for example, I gave you this wire right here, which was number 8 THHW, and I don't know what the terminal's rated for, so I'm not gonna tell you what it is. So we're just gonna have a maximum value because of the wire size, number 8, is gonna give me a maximum of 6 degrees Celsius as a wire capacity, right? At the end. Now, I'm gonna start with the value that XHHW allows me to have, which would be a 900 rated conductor, correct? XHHW, the double H means it's rated for 9 degrees. If I don't tell you if it's wet or dry, you don't have any way of knowing it. Let's just assume that that's in a dry location, so we don't have to worry about that. I've got derating factors because I've got this 98 degrees Fahrenheit value that I'm going to tell you to derate it based on, okay? So I'm going to use or start with the 9 degree column on page 187 or 189 because I've got the conditions I need. I've got a 9 degree rated conductor, dry location if it's a dual rated, and I've got a derating factor of 98 degrees Fahrenheit as an ambient temperature, okay? So I'm going to start with the value of the 9 degree column of number 8, which is 55 amps. Okay. Now, the 6 degree requirement that we're talking about up here is at the end of the calculation as a final value, right? So I'm not going to keep my eye off of that, but because this is a 9 degree conductor, I'm going to use whatever the maximum value I can to start with. So I'm going to start with the 9 degree column, which is 55 amps.
Well, where did you get the 98 Fahrenheit?
I just gave you the ambient temperature.
Oh, okay. Ambient
Right.
temperature. Gotcha.
I got it from Natural Fund, that's what Austin is supposed to be, so I just used that.
Okay.
Okay. Everybody with me so far?
Yeah.
All right, now, I start with the 55 amps. I go back to the table that's on page 185 or page 187. And if you look at this table, it's the very far right-hand column there. It has the values in Fahrenheit. So 98 degrees Fahrenheit on this smaller table would fall between that 96-104. Everybody see that? So I'm going to use the value that's under the same Celsius column that I take a value off of the other table. In this case, the 9 degree column is where that 55 amps came from. So I'm going to use the 9 degree column here at 91% as a derating factor. So that's going to be times 0.91. Again, I took this 55 amps to the 9 degree column, so I'm going to use a factor on the table there on the 9 degree column so they match up, right?
How did you get that .91 again?
From that smaller table.
From this in here?
And what I gave
This
you,
one over here, the 55. I got that.
yeah, you started with 55.
Then I came over here and I was looking at the 90.
Yep, but you're looking at 97 degrees Fahrenheit. So this is the ambient temperature value here, right? And that's why you go in the corner, 90 degrees Fahrenheit. So that put it right here. And then under the 9 degrees Celsius column, that's where the 91%. All right, so we're at 91%. So 91% of 55 amps is what?
50.05.
50.05. All right. So the capacity of that conductor is what? I'm gonna give you some options to pick from. That way, you get 25% chance, right? So I'm gonna give you 55 amps as answer A. I'm gonna give you 51 amps as answer B. I'm gonna give you 50 amps as answer C. And I'm gonna give you 40 amps as answer D. What's the correct answer?
D.
D. 40. And why is it D 40 amps instead of 50?
By the 60 degrees Celsius chart is the minimum, which is 40.
Okay,
you
so
go with that.
this row right here is where I ended up with this calculation, right? My calculated value came out to be 50.05 amps, right? Problem is that because of this rule here, putting me in the 6 degree column is maximum value because the determination, I end up with a maximum value of a number 8 at 40 amps. Does that make sense? It's a restriction from the front of the book that says, look, if I have a wire size is a number 14 through number 1, I can't assume more than 6 degrees Celsius value unless I know what the terminals are rated for, so on and so forth. But in this case, we didn't say anything about the terminals, right? So at the end of the day, even though my calculated value is this number here, it's not really useful to me because I'm gonna have to go to that 6 degree column as a maximum value for that number 8 just because of the size.
Oh, I got you now.
Mhm. 6 degree column.
Well, I know, but if you're already gonna be 40,
Right, that's
why
me.
don't you just, I don't know.
Well, because I need to see where it's at, because if I go
Make
below
sure.
40, then I have to use the below
I got
that,
you. I
right?
got
So I need to know where that calculation is in relationship to
Fine.
what that value,
Mm.
what the columns are. So that's a lot to remember,
sense.
right?
This will come into effect a lot more when you, do more than 3 carrying
We
conductors,
get that
right?
in just a second. Yeah, you're on the right path, right?
There's more.
There's more. But I want to make sure that we're clear with this, because this is probably the most confusing sticking point. If you can get this down, the rest will be a lot easier, right? What's happening here is that we're starting with the best value we can, the highest value we're allowed to give ourselves the best shot, right? If I can't use that 9 degree column to start with, fine. I use the 75 degrees, that's what they give me, whatever it might be. I'm dealing with Romex. Romex is, or type TW, it's not even rated for 60, so I may end up having to start with 60 and derate from there. But in this case, because this is rated for 9 degrees, it was a dry location, and I had derating factors to take into account, I'm going to be allowed to start with that higher value of this 55 amps. Had this been in THW, right? Then I can't even start with 55 amps. I can start with 50 amps because that's the maximum value for that THW under the 75 degree column. So what would happen here is I would have 50 amps instead of 55, but also look what happens if I go back to the derating for the ambient temperature under the 75 degree column for that same 90. It's an even bigger hit, right?
28.
So that same 98 degrees Fahrenheit on page 185 or 186, 187, is going to give me a value in the 75 degree column of, 0.88.
44.
What'd you say, 44 amps, Steve?
44.
Now, I'm still stuck with that maximum value from this row right here because I still didn't quite get there, right? So don't forget, in the rear view mirror, at the end of the day, you still have to make sure that you're not above either the 60 or the 75, depending on the wire size, right? In this case, that number 8 is in that section right there. The code book artificially says, look, you can't use more than the 6 degree value of the ampacity of that conductor just because of the size of it, okay? Make sense? All right. What if they told me that the determination that I've gotten in this question, if they told me I had THHW, and it was rated at 75 degrees Celsius for the terminals. They gave me that as a condition in the test question. That would change my answer on one of them, but not the other. Well, I actually changed the answer on both of them, but actually you would change the answer, period. But anyway, never mind. I'm going to start with the same approach. I'm going to start with page 187 or 189, because I still have to figure out, do I start with 90 or do I start with 75? Where do I go, right? Ask myself 3 questions. Number 1, is the wire rated for 9 degrees? Answer would be yes. Number 2, if it's dual rated, the question is going to be, is it wet or dry? In this case, I said dry, so I'm still good. I'm still a 9 degree hunt. Finally, do I have derating factors taken into account? Yes, the 8 degrees Fahrenheit is a derating factor. So that clears me to use the 9 degree value of this conductor as a starting point. So I'm back over here with this 9 degrees Celsius, 55 amps, right? Now, the calculation for the ambient temperature doesn't change. I'm still looking at the same 91% for 98 degrees Fahrenheit based off of the value of 9 degrees off that other table. So that doesn't change at all. So I still end up with 50.05, but the terminal rating of 75 degrees Celsius helps me because now I'm looking at the 75 degree column as a maximum value, not the 60 degree column, which in this case would be 50 amps, right?
Yeah.
So my answer then would be 50 amps, which would be answer C, if I knew this value right here.
If they said that.
If they told me that.
Yeah.
If they didn't tell me that, then the maximum allowance to assume would be that. Make sense? So you're gonna notice now, a lot of questions, they'll tell you, you have terminals rated for 75 degrees, and that's an important note when the wire is smaller, right?
And if they don't specify if it's a dry or wet, it's always gonna be dry, you assume it's dry?
Well,
Or-
that's a good question. I think the fair answer to that would be, you'd have to assume the worst condition, which would be wet, right? But I have not ever seen them do that. They usually tell you when
Specify.
yeah, or
Would
they
it be
use a
like
dash
with
too.
copper?
If you had, all right, let's stop there and let's look at the feeder real quick. If I had a feeder calculation, I don't have to worry about the 6-degree column, because remember, anything that's more than 100 amps or size 1/0 or larger, I'm allowed to assume 75 degrees right off the bat. I don't have to worry about this 6-degree nonsense, right? So let's say I had a 250 KC mill XHHW dash, well, XHHW. 250 KC mill XHHW. All right. In a dry location. And I'm gonna add one more thing. We're gonna use the same 98 degrees Fahrenheit as the ambient temperature. But I'm gonna tell you that I've got parallel sits in the same pipe, where I've got an A, B, a C, an N, an A, a B, a C, and an N, that are in the same pipe. Now, I'm just gonna tell you that we're not gonna count the neutrals, but that, and that are all current carrying conductors. I think everybody would agree, those are all current carrying conductors, correct? So in the same pipe, the same raceway, I've got 6 current carrying conductors. Here's the problem with that. You ever been in a, back whenever you were in high school, did you guys ever play football? You're in the middle, what is your, no, the freaking break in the middle, halftime. During halftime, you all go in there and you're still wearing your pads, and I mean, you're all packed into this little, back then, we didn't have air conditioners, I mean, they had one fan. The more people you put in that small locker room, the hotter it's gonna get, right? The more body or heat producing bodies that were in there, the hotter that place would be, and I mean, it would just make it worse, you'd just sweat even more than that. So think about it like this, if I put a bunch of warm bodies in the same combined area, I'm gonna have less of a chance to be able to dissipate that heat because of that confined space, right? So current carrying conductors, the more I have in the same confined space, the hotter the overall, temperature is gonna be, and the less effective the heat dissipation is gonna be, right? So if you look at the table, it's 310.15C1, which is on page 186, or in your case, page 188. The number of current carrying conductors that you're given free on the table is 3. Anything more than that, you have to derate for those additional heat-producing bodies that are in the same raceway. In this case, 6, which would be the first row of that table, which is anything 4 to 7, is it? 4 to 6.
4 to 6.
4 to 6 is 80%. So I'm gonna have a derating factor for this. I'm gonna have a derating factor for this. Each one of those is gonna be applied separately. All right, now the first question is the 250 KC mill XHHW, is that rated for 9 degrees? Yep.
Yes.
Yes. Is it in a dry or wet location? I said dry, so we're good there. And do we have derating factors to take into account? All right, so all of those tell me that I'm gonna use a 9 degree value, 9 degrees Celsius value at 250 KC mill, which is what, 290 amps?
290.
So we start with 290 amps. Because this came out of 9 degrees Celsius column, I'm gonna go back here to take the ambient temperature. I'm gonna use the 9 degrees Celsius column here. It's gonna be 0.91 again, right? So times 0.91 because of the 98 degree Fahrenheit ambient temperature under 310.15 B11, okay? And then I'm gonna go back and go, okay, well, if I got 6 current carrying conductors in the same raceway, that's gonna give me an additional derating factor of 80%. Times 0.8. All right, so 290 times 0.91 is
263.99.
63.9. Thank you. And then times 0.80.
211.12.
Ooh, 211. Wow. Really? 211 what?
1, 2.
Well. All right. So what's the final answer there? What's the maximum capacity of that conductor in whole numbers? 211 amps, right? It can't be more than 255,
So,
right?
200.
But since it's less than 255, which is what the 700 column is, then I'm gonna use the calculated value as maximum capacity. And I'm not rounding anything up or down. I mean, if they're asking for a whole number, it's gonna round down to 211 amps. Doesn't matter if that's 211.99, it's still gonna round down to 211 amps. 'Cause
and
it's
that's
that
them all
maximum.
combined, that's everything combined, right?
That's everything, that's the maximum value of that 250 kc mill. So if I have a service rated for 250 amps, that's not the right size wire, is it? Right? Okay.
So this was a feeder question.
Yeah, well, the 250 kc mill is gonna be a feeder. I wouldn't use it for a brain circuit, I don't think.
You
Unless it's,
could.
it could be a motor, it could be a motor brain circuit, right? I mean, it's possible, but, yeah, feeder question, I guess. Okay? Any questions on that? What if it was a wet location?
Oh, sorry,
What if this was not dry, but it was a wet location? This is where that issue with this dual rating XHHW comes into play, because it's no longer a 90 rated conductor, right?
You would go to the 60, right?
No,
Or
75.
Oh, yeah.
75. So in the case of the fact that I've got XHHW in a wet location, that is rated as a 75-degree maximum value, so that ends up giving me 255 amps as a starting point because of that caveat, right?
Yeah.
So I start with 255, and now I have to go back and get a different ambient temperature. Remember, I'm using the 700 column now, so instead of 91%, I'm using 88%. So 255 times 0.88. Now the number of current conductors is still going to be times 0.80, so that doesn't change. It has nothing to do with the wire capacity.
179.52.
179. Wow. 179.52. So that's maximum capacity of conductor 179.52. Now, the size of breaker for that. What would that size that breaker as? If I had 179.52 amps on a wire,
200.
200 amps. All right. So I'm gonna round this up. If I had a branch circuit or a feeder, 200 amps is the maximum breaker size. So yes, by default, I actually have a little bit more ampacity, I guess, if you will. But on a question that asked me the ampacity of the conductor, 179 amps is my answer. Right? That's not really I mean, if I've got a 200 amp rated service, if I have a 200 amp rated service, I cannot use that wire for a 200 amp rated service. Now I can round that up and protect it with a 200 amp breaker, right? But if I have a 200 amp load on a service where I've got a service that has 200 amps as a minimum requirement, that wire is not big enough, is it? I need to make sure that the load I have to carry is at least smaller than that, or equal to or smaller than the number of the wire capacity, and that's why this is important to know. I mean, the 200 amp rated service may be that I have 175 amps for the load, or 176 amps for the load, and I'm rounding it up to a 200 amp, that's why it's the 200 amp rated service. But if my load on that service is actually 200 amps,
You need a bigger.
that wire's not big enough. Makes sense? Okay. That's why it's important to understand the wire capacity piece by itself, because yes, you can round it up to a bigger breaker, but if you have a load that's rated 200 amps, then you're gonna have to have a bigger wire size. Okay. What if I had this same question here where I had everything except I didn't have but just 3 current conductors? So I've got this 250 kc mill XHHW in a dry location, and I only have this right here where I've just got 3 current conductors instead of 6. Just one last question. So 250 kc mill in dry location. So that tells me I'm allowed to use the 290. I'm doing 91%. That give me, what is it, 263 point?
Yeah.
What was it, 4?
91.
9? Yeah?
263.9.
Okay, I'm good with that. All right. So the maximum capacity of this conductor, and given this condition right here, which one of these 4 answers would be the best answer for you? Is it 290 amps, 264 amps, 263 amps, or 255 amps?
264.
Still haven't heard the answer, right answer.
For what?
I don't know how you get.
255.
It says 4 to 6.
255, why is that the right answer? Because that great big red line that you wrote on the right behind the
You go-
700
you
column
go
that
to the
said, don't you dare ever answer anything bigger than a 75-degree value of the wire capacity, no matter what. So be careful of this scenario here where you have a calculated value that didn't quite get there. yes, your calculated value is 263.9, but that's not the capacity of that conductor installed because the 75 degree rating in the terminal will drop that wire to 255 amps as a maximum value just because that's the maximum we're ever allowed to use. Right? So don't forget, as a final step, even when you're doing calculated values, you still have to go back and make sure that you're either at or below either the 75 or the 60 degree, depending on what the wire size is, okay? Don't forget that, that's really important. They'll give you some little derating factor like that and won't be quite enough to get you there and you'll fall for that 263 or 264 business. Because you're so worried about, do I round this up or down? Well, I'm not even worried about that, I didn't even get there yet. I'm at 255 because I can't be more than that no matter what, right? Now, if my calculated value would have been like we did a minute ago where we had that additional step, it was 211, right? That was less than the 75 degree value, so then my calculated value would have been my answer because it's the lower number.
Yeah, I got you.
Okay? All right. I feel like you guys got that pretty down pretty well.
How do you get the percent, how do you get the value of, if there's only 3 wires? How did you get that multiplier?
So if you look at the bottom of the table, it tells you that that table is based off of 3 current conductors. So I don't have to worry about it if there's no derating factor, if it's 3 or less. It's just.
Oh, so you don't gotta multiply it?
You don't have to worry about anything.
Oh, okay, cool. So
If I had
you
the
use
fourth
that
one
number. Okay.
Look, since you're bringing that up though, what did we talk, we were talking about, the conduit fill earlier, right? And we were getting some crazy numbers like 266 wires and stuff like that. Current carry conductors are really dangerous because look at the table that we're talking about here. After 9,
10 to 20, they go
What
into
happens?
multiples of 10s, huh?
Half.
well, I'm just saying,
After
50%, 35%.
if I put 10 current carry conductors in a raceway, what happens to my capacity of those conductors? I get gutted, right? 9 is the magic number. You're not going to be able to, I mean, 9 you can probably still use the same breaker size to be okay because most of the time you can take 70% and still be rounding up the same breaker size, whatever. But you get a 10th current conductor in a raceway, you're at half of the wiring capacity of that conductor. I mean, it's too big of a step. You're going to be changing your gear before you do anything else. So that's the problem with this type of installation here, and I've been hit with that before, right? I was doing a job at Southwest University in Georgetown, Texas, which is they have an engineering class there, and sure enough, they used the building we were doing as a field trip for the engineers, and one of those smart owners knew what this rule was, and they started counting the number of wires in each one of our 3/4 inch pipes coming into the panels, and sure enough, there was 13 current conductors in each one of them, which meant that now instead of 30 amps for number 10 and 20 amps for number 12, I'm at 50% of that number.
7.
Right? So, I mean, it's really an important rule. The maximum number of wires you can stuff in a conduit is not really the limitation that you've got to worry about. It's this one right here. That thermal layer, or that thermal issue of 10 current conductors, at 50%, you can't come back from that. You're going to be changing the breaker size, and your
What about
inspector's
if
going to
you-
hate you. Huh?
What about if you're not, like, if that was a gutter box and there's a bunch of MCs coming in and you got something like that? Does that still do the same thing? Is it still taking?
No, because we're
I
talking
mean,
about
they're going the
raceway,
raceway
right?
back, right? So it's just coming out.
So the gutter itself is not gonna be really our concern, because we're not gonna derate those
Okay,
based off
cool.
that. I mean,
Just
now, we
raceway.
would derate the MC if you bundle them together coming into it. And if you bundle the MC together for
But as long
longer
as
than
they're
24
separated.
inches, then maybe we'd have to worry, but if you rattled them together. Same thing with Romex, like if
They,
you
you know,
Romex.
they put a gutter box on the top and then they just throw a bunch of 3/4 down into the panel.
Yeah.
And a lot of times those are filled pretty tight.
Well, the 3/4 coming down from the end of the panel would be
That's where you lose it.
9, would be all you get.
Yeah.
And think about it like this. So I used to run 3/4 inch conduit, which 3/4 inch conduit you can get, I think, 16 number 12s in it. I think, is that right?
Sounds about right.
Or half inch.
Oh, wait, what?
Yeah.
No.
Yeah.
So
Seven.
my rule
Yeah,
of
16.
thumb is 3/4
That's like
inch
an
conduit and 3 full boats. Because I can put 9 current conductors, right, according to the table. I can put 3 full boats as long as I don't have linear or non-linear loads, and that's count the neutrals. If I don't count the neutrals, then 9 current conductors, 3 boats, or 3 full ABC with an N, ABC with an N, and it fits the conduit filling, it fits the maximum number of current conductors. If I go anything else than that, more than that, I mean, it doesn't really, I don't care if it's a 2-inch conduit, I'm still only gonna get 9 current conductors before I have to worry about derating the conductors. And that's probably the biggest thing to remember, is that it's not the conduit size that's really gonna be your limitation, it's the number of heat conductor conductors that create heat in a raceway. So ABC, in and in. I don't count the neutrals if they're linear loads because they just carry the imbalance like we talked about earlier. So then I'm just doing the ABC, that's 9, right? Anything more than that, it doesn't really matter what size conduit, I'm still gonna hit that 50% degrading factor of the impasse to that conductor. Okay, Romex. How many current conductors in a 12-2 Romex?
2.
2, right? Because the black wire counts and that white wire counts, right? What if I had a 12-3?
3.
2.
2.
Because I don't have to carry the white wire if it's a neutral, if it's just a multiplier. So here's what they talked about with Romex. Romex is actually stuck with the 6-degree column. So if you go back to 344 or 334.80, it tells you that you have to use as an overall jacket a maximum value of the 6-degree rated column for the overall capacity of a Romex conductor, right? Now, so I've got some number 12 Romex conductors. Let's say I've got 6 sets of 12-2 that are bundled together, coming in through the header, and my panel's down here, and from here to here I've got a distance of 28 inches. I've got them all bundled together, coming in one hole here, and right down in the panel in one hole. What's the maximum capacity of that conductor after it's all said and done? All right, what happens here is that in 334.80, even though it tells you the overall jacket assembly is a maximum of 6 degrees Celsius, it does tell you that you're allowed to use the 9-degree rating of the individual conductors inside the jacket as a starting point for your derating factors. So I'm allowed to use, when I'm doing the math here for Romex, a value for number 12 under the 9-degree column that's actually 30 amps. Right? That's important because that gives me a higher starting point. So even though this, is it 20 amps or 15? What is it in a 6-degree column for number 12? 20, okay. So 20 amps is my maximum value when it's all said and done. Because this article here tells me I'm allowed to use an 9-degree column to start with, I would start with 30 amps as my maximum value for that under the 9-degree column. Okay? Now, I don't know what the temperature is. If they don't give it to you, don't worry about it. So we're going to skip that first step because there's no ambient temperature listed, right? But the number of current conductors is how many?
6.
How many?
2, 4, 6.
12.
12. Yeah.
12, right? Because in each one of these pairs, I've got a black and a white, each one of them counts. So if I've got 6 pairs, I've got 12 current conductors, right? So I'm going to go over here to this table. I'm looking at this table looking, okay, well, if I take 50%, because I got 10 through 20, I'm going to take 50% of that 30 amps. So I'll multiply that times 0.5. And that's going to give me a value of, whoops, no, there you go. So now the maximum breaker I can put on that 12.2 on all 6 of those is going to be 15 amps. That's happened to me before, and the inspectors were like, oh, I hate that. How are you going to stop somebody from coming in later and put a 20 amp breaker on them? You can't. I mean, but I'm not worried about that. I'm only worried about what I have to do to pass this inspection, and that is 15 amp breakers is what's going to be in there. I mean, they'll tell you, well, you got to put a junction bar. No, I'm putting 15 amp breakers, number 12 wire. That's what I'm required to do by code. Whether you like it or not, that's really what the requirements are, right? I'm not required to do anything else beyond that. Tell the inspector that. You want to do anything else? You come out here and add that junction box.
Would you guys put like 15 amp receptacles too?
What?
So then you'd be putting 15 amp plugs and everything, I mean like all your
Yeah,
receptacles,
I mean, I could put a 20 amp on it if I
everything.
wanted to, because that's
Yeah.
a bigger value for a plug or receptacle, but yeah, 15 amps would be the maximum value of each one of the branch circuits.
Oh.
Now, there's a problem with that, because remember, I've got some 20 amp required circuits, don't I? Right? Anyway, that's a different story.
So they're actually, you're talking about bringing your Romex as your residential wire, right?
Yeah.
And when you drill your hole, you
Mhm.
run your wires through it.
Mhm.
The inspectors are degrading it.
Mm-hmm.
Wow.
Yep. So let's say you get smart and you know that 24 inches is the rule where that starts, because anything less than 24 inches, I don't have to worry about it. If I keep them separated for 23 inches at a time, then I don't have to worry about the derating factors, okay? So that's under the same section here under the article. If you look on page 4, where it says adjustment factors under C1, more than 3 current conductors. It tells you that adjustment factors shall not apply to conductors and raceways having a length not exceeding 24 inches. Or, let's see, where's the bundling? It says in here somewhere, basically, that I don't have to worry about taking an AC cable, blah, blah, blah. So, Yeah, well, just say that we, at 20, yeah, right, when maintain space continues length longer than 24 inches away, so most can go right, it's at the very beginning of that. So I got smart, so you know what, I'm gonna do this at 23 inches because I know what's gonna happen, so I'm gonna separate these. So this distance from here to here where their bundle is only 23 inches, right? I'm smart. Then the fire marshal comes in and says, well, don't forget to put fire caulk up in here, because you gotta make sure you have that thermal barrier, right? Son of a bitch. All right, so look at 334.80 real quickly, and what happens here is that 334.80 says, look, all this is great, we're having fun, but the minute you put thermal barrier or caulk in there, you automatically have to take the, it's on page 226, 334.80, it's like the second paragraph, where it says, where more than 2 NM cables containing 2 or more current conductors installed, not maintaining spacing, that's sealed with thermal insulation, caulk, or sealing foam, then passage of each conductor shall be adjusted in accordance with 310.15C1 or 310.14A2. And the exception shall not apply. The exception that we're talking about is the allowance of not having to derate anything that's less than 24 inches. So that thermal barrier right there that just got put in there automatically kicks in the derating factor, and I'm stuck with it anyway. Regardless of the spacing, I'm having to take that derating into account.
Oh, so repeat that again?
If I put thermal barrier in here or put thermal
Uh-huh.
caulk in here, it doesn't matter what the spacing is, I'm automatically still having to take the current barrier conductors
Oh.
calculation into account. So the 24 inches goes away.
Yeah.
Automatically, it doesn't matter if you maintain spacing or not, you're still gonna get hit for the number of current barrier conductors.
Dang. That's,
Okay.
Is that thermal caulking, is that code? Like,
Yeah.
you have, that's
Pretty much
residential too?
Pretty much, yeah.
Really?
Yeah, I mean, it's the headers were, I mean, if you get flames inside that bay, I mean, it's gonna be a draft.
I can feel it.
We're gonna run in the attic. Most of the time nowadays, you see them drill separate holes in the header, so it's really not that big of a deal, but you're still gonna be stuck with, what, 4, I guess is gonna be the maximum? 4 in any one given hole, cause that's 8 current conductors, that's still 70%. That'd be enough for us to round it up to 20 amp breaker. But if you get that 9th one, if you did 5, then you'd have 10, that's too many, right? So 4 would be the maximum you put in one given hole. And then you can put thermal caulk in it and still take the reading, it's fine.
So they revised that? They revised that code?
What's that?
The 334.80? It says deletion, text deletion and
What?
favorite table revision.
What? Wait.
The triangle?
Yeah.
You talking about 334.80?
Yes, sir.
What are you saying?
So it said, did they like, delete something then or change it?
No, so the delta just means there was a minor change. And so if you look at that gray highlighted at the bottom where it says the exception shall not apply,
Oh, okay.
that's all it means. No, it didn't change, it's been the same. 334.80 is a special condition that has to do with Romex, and so it really, it's got some special rules. It wouldn't hurt to read the whole thing if you had a chance, okay?
Okay.
All right, well, it is almost 6 o'clock. I promised you I was gonna be done pretty close to that. The last thing I have to tell you about, right, is remember that the values that you're looking at on 310.16 are really, think about it like this is kind of a commercial, if you will, right? If I'm dealing with a residential feeder, residential services don't have the same intense demand as a commercial set of buildings do, right? We don't really expect every light to be on in the house because we don't really use it that way. We expect people to kind of move from one room to another. They kind of turn stuff off as they go in or out, right? So the amount of diversity, I guess, you can have or allowance for a residential dwelling is a lot less of an intense requirement than what you have in commercial. I will not use this table to size a feeder for residential dwelling. They used to have a table back in the day, it was 310.7, I don't know if you guys remember that or not. Then they took it out of the code book in 2014 and caused a riot. For 3 years, nobody knew how to calculate the crap all of a sudden. It was crazy, it was the craziest thing I ever saw. And even the teacher had it wrong. I mean, and they have one example in Annex D5A that was really poorly written, it was horrible. So then the next edition, they brought it back and they put it in the
17.
index, or the annex in the back. And then finally they got smart and they put it back, but now that's under 300.12. So I do want to point out 300.12 is no longer 300.7, but the table, thank God, is back in the code book. It's on page 183 or close to thereafter. 310.12A.
310.12, dwelling service and feeders.
310.12A. Right there. Thank God it's back, because we really lost our crap when that thing disappeared. I'm telling you. Now the math that they give us for the degrading factor is still there. It's still talking about the 83%, but I'm not gonna go into it because, I mean, the table's there, that's all you need to know. But if I'm dealing with a residential feeder, use this table, not 310.16 to size that wire, okay?
What table is it?
310.12a. So if I have a load, I'm gonna walk you through this, will be the last thing we do real quick, and this will help you kind of see how this works, right? So I'm dealing with residential service. I've got a load calculation, I've gone through and done all my demand loads or demand factors, we've got demand loads for everything. And I end up with a value of, let's say, 38,500 or 500 VA, or watts, excuse me. So that's my total calculated load that I've got for all the stuff that's in the house, right? So I'm gonna size the service based off that number. First thing I'm gonna do is take the 38,500 and I'm gonna divide it by 240 volts. Nominal voltage rating for a residential dwelling. That's gonna give me a capacity that I've got to use, so then we're looking at 38.5, did I say? Yeah. Divide by 240. All right, what do I do with that? 160.41. Well, that's not a standard service size, is it? So we need to round that up to whatever the next standard size
175.
breaker would be.
175.
So 240.6 is the table to go with that, and yes, the next standard size up from that is 175. Don't ever try to remember these things because there's a little table that's 240.6A. Just go back and make sure you look it up because you'd hate to put a breaker size that doesn't exist because they do make a 45, but they don't make a 55, right?
You said 240.6A?
240.6A.
I installed one, that's the first time I saw 175. I didn't even know they made 100.
Yeah, I know, right? Well, they make a 110, right? It used to be one they used for apartment complexes and stuff quite a bit.
A lot of newer houses are 175 now.
Really?
All right, 175 amps, right? So what happened was, this is my load value. This is minimum size service conductor, or minimum size service size, right? So that right there, because I'm not gonna have a breaker that's 160.41 amps. I'm gonna have to round that up to the next standard size breaker. So 175. And then I'm looking at the table here, page 140, or 183, 310.12a. I'm using this table then at the 175 amp, it'd be in a 1-aught. So I end up with a 1-aught copper feeder based off of that table, okay?
You couldn't have got all that just off that single phase dwelling, just off that 310-12?
That's what I'm doing.
Oh, okay, I thought you
Basically,
were
I
using
gotta figure out what the amps are first, right? Round up the standard size, which is the next breaker size up, basically, is what that is. So that 175 then brings me that table there.
The copper, so you got the one.
Yeah, 175 amps would be what I would be looking at on that table. For
You always want to double check, right? Or is that,
Hmm?
you always want to like double check. That's why you did the long
The
one?
240.6?
Yeah.
Yeah, because I just want to make sure I got the right breaker size, right? Or make the service size. I mean, if there's another breaker, obviously, yeah, you're right.
Because when you got the math off of it,
You're
it
right,
showed you
okay.
right there, right?
You're right, yeah.
I was just saying, man.
No, you're
I was
right.
looking for the other one, I couldn't find it.
Okay, he's right. You could just use the 175, I mean, obviously, because, I mean, at 160.41, you're too big for the 150, right? So, go home. A good point. I think I wanted you to know where this other table was, just,
Yeah.
right. Anyway, 1-aught, right? What size grounded conductor would be the minimum size grounded conductor for that table? Now, so remember the neutral conductor, the reduction that's allowed on the loads that are in this house, so the parts that are in this 160.41, I'm allowed to take a 70% less value for the range and the dryer, right? But remember, loads that don't have a neutral load, like your electric heat, doesn't have a neutral load, nothing. Sometimes the biggest load in the house is electric heat, right? So when I'm doing my neutral calculation, I'm looking at all of the break circuits that are 120 volts, so all of that gets added in there, but that's usually smaller values. And then 70% of the range in the dryer, the water heater and the electric heat's not even added, right? So a lot of times your neutral calculation is a pretty small value, but no matter what, I can't have a neutral conductor less than the value that's shown on the table that is 250.102C1. Because remember, that is a grounded conductor minimum size table based off the wire size. We're technically at 250.102C1, even though it's the same table basically. I'm looking at a 1-aught, right, copper? Number 6. or my actual calculated value for the neutral based off of, manually going through there, which, what did you say was the number what? Number 6. Number 6. Okay. Any questions? All right, I think that's it for today. If I did any more than that, you guys would revolt and be mad.
Well, let's get room here.
So, there's not any, I tell you.
I got it.
I don't understand this whole solar thing that everybody's so excited about, but man.
Well, it's because most people didn't get it. We got it in October last year. And so it's like, Texas did.
No, they're supposed to be like the.
No, I'm not saying that's what the whole frenzy is about, is that if the next time will be like in 100 and something years.
Oh, but they're supposed to be like double the population down this
Yeah,
weekend just
because
because of that.
nobody else gets, a lot of people don't get it.
But then
We're right in the pathway of like,
I'm gonna
Well, we're
sell
only
seats in my front
getting
yard.
9 minutes of it.
yeah.
Like, you gotta go to other
Yeah.
parts of the United States and you'll get like.
What
There's
they,
some people
is it
that
90?
drugs.
Oh,
Yeah, we're only
They
getting
have
like
that
one,
little
like,
problem
one
scale.
thirty or
Is that what it is?
31 or 40 or something is what we're gonna have.
Well,
And it's supposed to be cloudy.
It's gonna get totally dark?
Yeah.
Cause I know in October, it was, or it was October, November. it was
Well, you can see the
for like
clouds
3
get
4
dark.
hours. It stayed.
Yeah. Yeah, they were
I see
saying
that
like
it's
the
already
darkest
run anyway, so
will
we're
be
gonna
by
drive
9
all the way
minutes
to
span.
That's
Texas
crazy.
for that.
Yeah.
See y'all at 8:30 in the morning.
7:30?
8:30.
Oh.
Thank you.
Yes, sir.
We'll see you in the morning.
I'm so proud of you.
I didn't mess it up, man. I didn't mess it up.